Hello, hello. I am going to just make a quick, and I say quick, I'm sure we'll end, at like 20 minutes from now, but a quick video just walking you guys through some of those bonus questions. So remember, any of them with the secant, cosecant, or cotangent, only do those once you feel comfortable, if you feel comfortable. Maybe you might try some over the weekend leading up to the test. In case there's a bonus question on the test that involves one of them. But it won't be one that will count against you in case you get it wrong, which I doubt you would, but just in case. All right, so I'm going to start with number 3. So I'm going to work out number 3, and then I'm going to pick one of the harder ones as well. So, and by harder ones, I mean something that's going to require factoring, really, as hard as we're getting. So on this first one, number 3, the first thing to look for here is always going to be whether or not you have any like terms. So we talked about like terms, how to identify them. So cosecant squareds are alike, so I'm going to combine them. So as I do that, I just want to let you guys know that as we work through these problems, even though they are cosecant, everything is basically exactly the same until the very last step. So notice I'm subtracting and I am getting a 1 left over. If I have 3 of something and I take 2 of those things away, I only have 1 cosecant squared of theta left. Okay, so far, exactly how we would solve if it was sine, cosine, or tangent. And then remember we talked about the cosecant squared really just means the cosecant of theta squared, and that has to equal 1. So when we're solving this algebraically, we will now take a square root, right? We're taking a square root. And the square root of something squared, because those are inverse operations, they cancel each other out, leaving us with just the cosecant of theta on the left. On the right, don't forget, when you are putting a square root into a problem that wasn't already there, right? This problem didn't have any square roots in it until we put it there. You have to assign both positive and negative 1. Well, positive and negative whatever, but in this case, positive and negative 1. So I just want to stop and talk about that for a second, because this only applies when we introduce the square root, because we're undoing a square. So if you look on the same homework, if you look at number 5, for instance. So number 5 already has a square root in it, so you don't put plus or minus. You only do that when you are the one putting the square root sign in, not if it's part of the problem. Okay, so now we do exactly what we would normally do. We say theta then is going to be the inverse cosecant of positive or negative 1. The inverse cosecant of positive or negative 1. So far, everything's the same. The problem is cosecant isn't one of the coordinates, right? It's a reciprocal of the coordinate. Specifically, it's the reciprocal of sine, right? The cosecant is the reciprocal of the sine of theta. And that's important because I can rely on this piece of information to help me solve this problem. I'm going to make this a little bit easier. And by that, I'm going to change some stuff over here. So I'm still solving for theta, but the cosecant inverse, the reciprocal of the cosecant inverse is the sine inverse. And I'm allowed to do this as long as I also take the reciprocal of this number, whatever the argument is. So reciprocal of a number, remember, we're just flipping the fraction. So it's 1 divided by 1. If I flip it, guess what? It's still 1. So we still have positive or negative 1. Obviously, it's not always going to be exactly the same. This one's special. So we'll do another one in a second to show you what happens if it's not a 1. So by solving now this equation, it's going to do 2 things. Of course, we get to solve this equation, but it's also going to solve the original one. So if you see a cosecant or a secant or a cotangent and it's scurry, don't worry about it. Just think of it in terms of reciprocals. Just apply it to both pieces. So now we know this is much easier. This is looking for any angle on the unit circle that has either a positive or a negative 1 in the y spot. And if there's a positive or negative 1 in the coordinate, we know the other coordinate has to be 0 if it came from the unit circle. So what are going to be the angles that have this setup here? Those are going to be our answers. So theta would be, the first coordinate I would say is 0, positive 1. So where is 0, positive 1? That's pi over 2. And then second, 0, negative 1, that's at 3 pi over 2. And we are done. So by solving this equation, the one I put a star next to, by solving it, getting these two solutions, it's actually solving this one as well. It's as easy as that. So let's try number 4. So number 4 is a squared. It's secant squared of theta minus 6 is equal to negative 4. So again, I don't have any like terms with my secant squared like I did up in number 3 where I can combine. The only thing this time I'm going to combine are the constants. They are alike, right? Numbers are alike. So I'm going to add 6 to both sides, and I get the secant squared of theta equals negative 4 plus 6 is a positive 2. All right, and we just talked about if it's squared, we need to apply a square root. So this equation becomes the secant of theta, right? Because the square and square root are inverses, they cancel. And that's going to equal plus or minus, because I introduced this square root, and I'm just going to keep it the square root of 2. I don't want a decimal, right? We don't have any decimals on our unit circle. So I want to keep it as the square root of 2. It's fine, right? It's fine. We can do a square root of 2. We're geniuses. All right, so next I'm going to isolate theta, right? That's my job, is to solve for theta. So I'm going to do that by taking the inverse secant, the arc secant of both sides. It cancels the secant on the left, leaving me with theta on the right. I end up getting the inverse arc secant of plus or minus square root of 2. And that looks scary, right? Square root of 2 is not on our unit circle. There's something close to it. So let's see if we can find that something close to it. So just like we did above, the cosine is the reciprocal of the secant. So I can rewrite the secant inverse as the cosine inverse as long as I also do the reciprocal of this number. So if it's the square root of 2 over 1, it's anything can be written over 1, and I flip it, I get plus or minus 1 divided by the square root of 2. Oh no, I put a square root sign in the denominator. That's a no-no. I need to fix it. So we do need to rationalize this. So don't stop here. What I've seen previous students do is they see a 1 on top and a 2 on bottom, and they automatically say that's 1/2. But I promise, 1 divided by the square root of 2 is not equal to 0.5. Don't believe me? Try it. It's not equal to 0.5. So we can't treat this as a 1/2. So 1 divided by the square root of 2. I know it's plus or minus. We'll put that back whenever we put it over here. I'm rationalizing by multiplying by square root of 2 over square root of 2. And I get root 2 on top divided by square root of 2 times square root of 2. Square root of 4. Square root of 4 is equal to 2. So theta is the inverse cosine of plus or minus square root of 2 over 2. Holy cow, that equation became so much easier now, right? This is saying what angles on the unit circle have an x coordinate of either positive or negative square root of 2. I can think of a whole bunch. So theta is going to be all of the pi over 4 coordinates, right? The pi over 4 coordinates are the ones that have root 2 over 2, and we know that the y coordinate must be root 2 over 2. But I'm allowed to use positives and negatives. So I'm going to move in quadrant 1, it's a positive root 2 over 2. In quadrant 2, it's a negative square root of 2 over 2, and I'm okay, I can have a negative, so it's 3 pi over 4. Quadrant 3 is also negative, so that's going to work. We've got 5 pi over 4. And then finally, we can move all the way into quadrant 4 where it's positive again. So we have 7 pi over 4. And here are our answers. So by turning something that's unfamiliar into something we are more familiar with, it makes our life a little bit easier. So we did that today when we factored trigonometric equations and we turned them into quadratics, right? If we treat it like something we're more familiar with, it makes our brains work a little bit easier. All right, so I'm going to do one more. I picked one of the harder ones. It's number 7. And this one is a definite harder one. This is a star. So if you are not ready for this, pause the video, come back and visit it later if you would like to. We'll have the conversation tomorrow as well. But this one is a doozy. So that's why I wanted to work it out for you guys. So I could have been writing this the whole time I was talking. So 2 times the cotangent of theta minus 3 secant of theta equals the cotangent of theta times the secant of theta. No, we're not done. We still have minus 3 secant of theta. Whew. That's a lot. That's a lot. And don't neglect that first step. I know these can look overwhelming. So always stop and just identify what terms are alike and combine any like terms that you can. So I have a cotangent. I see cotangent again, but he's married to secant, so I can't combine those two. Same thing with this secant. I can't combine the secant with this one, but look, there's one over here. So these two can be combined. So I'm going to move, let's move this one. And when I put it over here, just so happens, boop, boop, they both go away. They both go away. So now we are left with square root of 2 times the cotangent of theta. So this is another example where the square root was part of the problem. I don't want to put plus or minus. I just keep it. And now that's the only thing left on the left side. And the right side just has the cotangent of theta times the secant of theta. All right? So we combined like terms. Next, we want to look to see if we can factor. So the previous examples, we only had one trig function left. So we just had one word, right? One word, and then the rest of the stuff was numbers. So now I have words on both sides. So I have to do something different. Got to do something different. And normally that different thing that your brain is trying to tell you not to do is factoring. Factoring is so fun. So before we can factor, we need this to equal 0. We've got to have it equal to 0. So I need to choose one side to move everything to. Because I don't have anything squared, it doesn't really matter which side I choose. So I'm going to move stuff over to the left. So I'm subtracting this whole chunk over to the left. So I get square root of 2 times the cotangent of theta minus the cotangent of theta times the secant of theta. And because I subtracted him over here, he canceled, and there's a 0 over there. All right. There are things that I see my sweet babies do when they aren't focusing. Don't subtract these cotangents from each other. You can't do it. It's not like, oh, well, I'll just cancel them. And then look, it's much easier. That's illegal. Because this is not just a plain cotangent. He's married to secant, so you can't subtract them. Another thing I see my sweet babies do involved division in this step. You are not allowed to divide by a word. Let me say it that way. You cannot divide by cotangent to get it to cancel. That's illegal. Don't do it. Factor it. Anytime your brain says, oh, there's a cotangent on both sides, let me just cancel them. That's a factoring hint. Factor, factor, factor. Now, this is not quadratic factoring. We don't have to do factoring or quadratic formula here. This is GCF factoring. GCF factoring. I'm only allowed to factor when it's equal to 0. I've got that. Now I just need to identify the GCF. So what do we see that's alike in both equations? It's cotangent. So when I factor using a GCF, I write the GCF in front of a set of open parentheses. Okay, and then in these parentheses, I'm going to write whatever is left when I take cotangent away. So 2 times cotangent of theta, if I factor cotangent out, I get a square root of 2 left over. Minus, I'm factoring cotangent away from cotangent secant. So secant is left. Now that I've factored, either by GCF factoring or quadratic factoring, if it was that type of problem, now you're ready to use the 0 product property. That just means take the first factor, the GCF, and set that equal to 0. And then take the second factor, square root of 2 minus the secant of theta, and set him equal to 0. And then we're going to solve each of these equations individually. Okay? So for this one, I would just say theta is the inverse cotangent of 0. We're going to come back to that. Let's do the same thing over here. This one needs a little more work. Okay? So I'm going to add secant to the other side. So I have the square root of 2 equals the secant. I'm just going to write it in the way I like. I'm just swapping them. The secant is equal to the square root of 2. So theta would be the inverse secant of the square root of 2. Wow, that one sounds familiar. It's almost like we just saw something just like that. So I'm going to go ahead and finish this one just because it's fresh in our brain, right? Just from number 4. So we said if we're solving a secant, an inverse secant, we can change it to its reciprocal as long as we change this to the reciprocal. So it was 1 divided by the square root of 2. Now this time it's only positive, right? That square root was already there. I didn't put it there, so I can't put positive or negative. I'm only using the positive. We then rationalized, and we knew that this was root 2 over 2. So now I'm only pulling the angles that have a positive x-coordinate. So it's all the pi over 4 angles that have a positive x-coordinate of square root of 2 over 2. So cosine is positive in quadrant 1 and quadrant 4. Quadrant 1 and quadrant 4. So I'm keeping pi over 4 from that list, from number 4 that we just did, right? If we look back, it was right here, right? Pi over 4 works. 3 pi over 4 is not in quadrant 4. 5 pi over 4 is not in quadrant 4. So the other answer here is 7 pi over 4. Okay, so we've solved this side. So again, like I mentioned, a lot of these are going to be repetitious because there's only so many angles on the unit circle. So it's really just repeating, just putting the equations together in a different way. All right, so now we need to finish this side, right? We haven't solved for theta, we just set up our equation. So there's a couple different ways to think about the cotangent. You can think of it as the reciprocal of tangent, but really the cotangent, we can think of it as the reciprocal of tangent in terms of the quotient, right? Tangent is y divided by x, cotangent is x divided by y. And if I want the answer to be 0, right, I'm looking for the angles that when I do this, the answer is 0. We talked about if the answer to, if the quotient is 0, right, if the answer to this is 0, 0 must be in the numerator, not in the denominator. So we know that 1 should be in the denominator. Or negative 1, right? Because those are the coordinates. If we know there's a 0 in our coordinate, then we know it's either positive or negative 1 for the y value. So now we just need to know what angles fit this pattern. So 0 positive 1 is pi over 2. Why can't I make a 2? 2. And 0 negative 1 is 3 pi over 2. So these should be answers as well. However, there's something weird that happens once we start working with a secant, a cosecant, the tangent also, the cotangent. Because if you think back to that big table from before we went on fall break, the infamous table, do you remember how some of the answers in that table were undefined? And they only happen for secant, cosecant, tangent, and cotangent. So there are some angles that make these functions undefined. And if we include them in our answer set, and they happen to make one of the functions undefined, it means the angle's illegal and it's not allowed to be part of the solution set. So anytime you are solving and you're working with one of these 4 functions, here's what you do. It's not hard. It just requires checking your answers, which I know you guys hate doing, but it's really, I'm going to show you the easiest way possible to check your answers. Do you see how these 2 angles came from the cotangent? So we know that they are not undefined on the cotangent. But we need to check the two angles from this side with the other function on the other side. So I'm just going to say, what's the secant of pi over 2 and the secant of 3 pi over 2? And I just want to know if they're undefined or not. If they make this undefined, I'm not allowed to circle them. They can't be part of my answer. So let's try it. The secant of pi over 2. So the secant is the reciprocal of the x coordinate, right? It would be whatever x is, we would flop it, so it's 1 over x. Well, the x coordinate of pi over 2 is 0. The reciprocal of 0, 1 divided by 0, is undefined. So because this is happening when I plug pi over 2 into the other function, right? It doesn't matter what it equals. It can't be undefined. So I know it's not equal to the square root of 2. That's okay. I just don't want it to be undefined. If it's undefined, like pi over 2 is, you have to cross it off. It's not allowed to be in the circle. He's illegal. So let's do the same thing with 3 pi over 2. So it's the x coordinate, the reciprocal of the x coordinate of 3 pi over 2. That's also 0. So we have 1 over 0. This is undefined as well. Oh no. 3 pi over 2 is also illegal. All right, so we take the two angles from the cotangent solution and we check it on the secant. Now let's take the two angles from the secant and check them on the cotangent. So is the cotangent of pi over 4 defined? It doesn't matter what it is. It just can't be undefined. And then we're also going to check it with 7 pi over 4. So see how I took the two answers from the secant and plugged it into the cotangent? And I took the two answers from the cotangent and plugged it into the secant? That's how I'm checking my answers. So the cotangent of an angle is the x coordinate divided by the y coordinate, right? At pi over 4, the x and y coordinate are exactly the same. So when I divide them, when I do x divided by y, the answer is 1. And that's okay. It doesn't matter what it's equal to as long as it's not undefined. So pi over 4 is good. He's allowed. I don't have to cross him out. Pi over 4 is good. I'm going to try it on 7 pi over 4. Again, it's x divided by y. Because we're in the fourth quadrant, x and y are the same, but one of them's negative, so the answer is -1. Again, that's okay. It's okay. It doesn't matter what it's equal to as long as it's not undefined. So both of these angles are good. This is the only two angles that I'm allowed to use to answer number 7. The ones that we crossed off have a special name. I'm going to give you a second, see if you can remember. What is the name of a solution to an equation that works when you solve it algebraically, which is what we did. We solved this algebraically. But for some reason, it makes the function undefined. What are those called? So these two angles, I feel like I'm like Dora the Explorer right now. Hopefully you knew that these two angles are called extraneous solutions. And it's very common for that to happen in math class. So it's important that you check them. Now that's only a problem if you're working with these four. If you're working with sine or cosine, they're going to be defined no matter what. There's never a time where sine and cosine are undefined. All right, so hopefully you found this video helpful. Again, these problems that I've worked out are just bonus problems, extra, just to see. Again, I want all of you to feel challenged. So this will get that job done. It will definitely challenge all of us. So tomorrow, make sure you're asking questions and you come to class with any issues that you guys had. If you weren't getting the answers from that answer key that I attached to your homework assignment. Okay? Hasta mañana.